Welcome to my class on measures of dispersion. In this video, we shall be looking at a lot about measures of dispersion, starting with the definition of a measure of dispersion. So, a measure of dispersion is a statistical measure that describes the gap between data entries in a data set and a value produced by a specified measure of central tendency that is often the arithmetic mean. So, what does this mean? Take note, in my illustration I gave during the course of teaching you measures of this central tendency, please take note of the fact that a measure of central tendency was described to be a statistical measure that will produce a representative value for the data set. Now, producing a representative value for the data set simply can be compared to producing a governor for a state, producing a president for a country, producing a class rep for a class. And take note, whenever someone is elected into office, appointed into office, or selected, as the case may be, to represent an entire class, people would often either complain about his or her leadership, or people will complain, or not complain rather, about his or her leadership. So there are some people that will consider it as being a fair leadership, a good leadership, and there are others that will consider it a bad leadership. That process of comparison, making comparison between the data entries in the data set or people that are being represented and the person representing them, can be compared to a measure of dispersion. So if a measure of central tendency will produce a representative value, for example, among these 5 persons, if we select this guy to be the representative value representing the entire data set, then this must have been done by a measure of central tendency. So it is the job of a measure of central tendency to produce this guy. So the measure of central tendency can be compared to an electoral process. It can be compared to an appointment process that produced this guy. But once this guy is produced to represent the entire data set, then comes the job of a measure of dispersion. It is now the job of a measure of dispersion to evaluate the gap between this guy representing the entire set and everybody here in this data set he's representing. So it could be some of them out of the lot will consider their gap between their gap from this guy to be so close, implying that the leadership of this guy is good to them, whereas some that are far away from him will compare his leadership as being bad. So let's consider in statistics what are some of the measures of dispersions available. Some of the measures of dispersion available are: 1, we have the range; 2, we have the mean deviation. 3, we have the absolute mean deviation. 4, we have the variance. 5, we have the standard deviation. 6, we have the interquartile range. 7, we have the semi-interquartile range. And 8, we would also be discussing the coefficient of variation. So these are some we shall focus on in this study: the range, the mean deviation, the absolute mean deviation, the variance, the standard deviation, interquartile range, semi-interquartile range, and the coefficient of variation. Now let's start with the range of a data set. So the range of a data set R is computed with the formula largest value in the data set minus smallest value in the data set. In other words, the range is the maximum minus the minimum. So how do you compute the range? The advantage of the range as a measure of dispersion is that it is very easy to compute using just this formula. So if I have an example 1i that asks you to obtain the range of the values 8, 1, 4, 5, 6. And 2, obtain the range of the values, obtain the range of the values 9, 4, 3, 2, 7. Now, notice that to compute the range would require you, in this instance, to simply say largest value 8 minus smallest value 1, and that gives me, of course, the answer 7 as my result. In this instance, the range R will be largest value 9 minus smallest value, in this case 2, and that will give me 7. And that brings about the advantage of the range. It is very simple to compute. All you have to do to compute the range is identify the smallest value in the data set and subtract that value from the largest value in the data set. But this brings about a serious problem, the problem of bias. You will notice that the range goes into a data set considering only extreme values, the largest value and the smallest value. So imagine you being in your home and your father or mother wants to give a gift, and the gifts available are just for the eldest, which you may not be, or the youngest, which you may not be. So if the gifts available in the house from your father or mother to you guys is only for the extremes, that is the eldest versus the smallest, not considering you in this instance, let's assume that you are not the extreme, okay? It means that there is a sense of bias. On what basis do you consider just the extreme values, the largest and the smallest? And that is the major problem of the range. Another problem of the range is that the range appears not to be unique. Notice that for these two different data sets, we are getting the same range. And it will make it look like this range is coming from this data set and this range is coming from this data set. So the data sets may be different, but the range remains the same in this instance, telling you that the range is not unique, okay? So that being said, let's move on to the next measure of dispersion, which is the mean deviation. In the mean deviation, we shall be overcoming the problem of the range, but let's see what the advantages will be for the mean deviation and also the disadvantages thereof. The mean deviation can be computed with the formula MD equals summation from I equals 1 to n xi minus x bar all over n, or it can be computed with the formula MD equals summation from I equals 1 to n fi xi minus x bar all over summation fi. Okay, so the mean deviation can be computed with this formula. What is the difference between both of them? This one is appropriate for computing the mean deviation when there are no frequencies in your data set. That is when data entries in the data set do not reoccur. But as soon as you have data entries in the data set that reoccur, please, it will be advisable for you to go with this for easy computation. Now, what is the advantage of the mean deviation over the range? Unlike the range, the mean deviation considers every data entry in the data set. So quickly, you can see that, unlike the range, it is not that biased. It considers everybody in the data set if there are gifts available. But for the range, it only considered extreme values. So I'm going to add one more example here to cater for frequency. So let's start with using the formula to compute the mean deviation. As my solution for number 1, the mean deviation MD will be the summation of all these divided by number of data entries you have to get the mean, and I'm going to subtract that mean from each of the data entries. So let's compute the mean. 8 plus 1 will give you 9, 9 plus 5 will give you 14, 14 plus 6 will give you 20, and 20 plus 4 will give you 24. And 24 divided by 5 will give us our mean. So I'm going to put not our mean deviation, but our mean. So this will be 24 divided by 5. And 24 divided by 5, 5 in 20 is 4 point. 5 in 40 will give you 8. So this will be 4.8. Now I'm going to subtract 4.8 from each of my data entries. Okay, adding all of them. So this will be 8 minus 4.8. Get your mean, subtract your mean from each of your data entries. So that's what I'm doing. 1 minus 4.8 plus 4 minus 4.8 plus 5 minus 4.8 plus finally 6 minus 4.8. So this will be my numerator. I'm going to bring this down, and divided by 1, 2, 3, 4, 5 data entries. So divided by 5. Let's put this by the side. So let's see what that gives as our result for the mean deviation. Now let's simplify this. So we have 8 minus 4.8, which gives us 3.2, plus in bracket 1 minus 4.8 gives us minus 3.8, plus 4 minus 4.8 gives us minus 0.8, plus 5 minus 4.8 will give us minus will give us 0.2. This will give us 0.2, and 6 minus 4.8 finally will give us 1.2. So when you add all these, you would end up having 0 divided by 5, which will give you 0 as our result. So it tells you that the mean deviation in this case is 0. Let's compute the second example. Okay, so in the second case, we are asked to find the mean deviation for this particular problem, the mean deviation when you have 94327. So what's the average of 94327? That is the mean of 94327. So I'll quickly compute just by the side here. The mean of 94327 will be 9 plus 3 is 12, 12 plus 2 is 14, 14 plus 4 is 18, and 18 plus 7 will give me 25. So this will be 25 divided by 5, giving me 5 as my arithmetic mean. Okay, now I'm going to come over to the mean deviation and obtain the mean deviation by subtracting all this in sum divided by 5. So everything divided by 5. Let's see. So 9 minus 5 is what I have here, plus 4 minus 5, plus 3 minus 5, plus 2 minus 5, plus 7 minus 5. So that would end up giving us 9 minus 5 is 4. 9 minus 5 is 4, plus minus 1, 4 minus 5, which is minus 1, plus minus 2, 3 minus 5, plus minus 3, 2 minus 5, plus 7 minus 5, which is what? 2. And all these will be divided by 5. Clearly, you would also notice that the numerator gives 0. 4 plus minus 1 plus minus 2 plus minus 3 plus 2 will give you 0 divided by 5, which gives you 0 as your mean deviation. So what does it mean? It means that in both cases, we've gotten our mean deviation to be 0. But take a look at this. The reason why you get your mean deviation as 0 is that the sum of all deviations from the mean should amount to 0. And the mean deviation therefore has a major disadvantage in the sense that it gives you the impression that there is no dispersion in the data. And that is coming from the result that all the sum of all deviations gives you 0. So it is not a true picture of what the dispersion is in the data set. As such, that is a major disadvantage of the mean deviation. Painting an all is well situation about your home, whereas there may be one little problem or the other in your home. So the disadvantage of the mean deviation does not erase its little advantage. It is also easy to compute, as you can see, and it also uses every member in the data set. To overcome the disadvantage of the mean deviation, we'll be looking at the absolute mean deviation. But let's compute one more problem, in which case we shall be considering a data set with frequencies for the mean deviation. If you are given a data set with frequencies, how do you compute? Let's see. Now, to compute the mean deviation of this data set, you will notice that in this data set there are frequencies. So all I have to do will be to say mean deviation will go with this formula from I equals 1 to n fi xi minus x bar. So x bar is the arithmetic mean in this case, and the xi's are the data entries in the data set, and fi represents frequency. To solve this problem, it will be best you go with using a table. So I'm going to put up this table, I'm going to put up this table, this. Okay? So, in this table, I'm going to do the following. In this table, I'm going to put here xi, in which case I have 3, I have 2, I have 4. Irrespective of the fact that 4 repeats itself, just put 1 because there are frequencies. So I have 3, which occurs 1 time as my frequency. So 2 occurs 1 time, 4 occurs 3 times. So then go to the next value, which is 5. 5 occurs 1 time. So I'm going to put 1 as my frequency. Okay. Then I'm going to put up 8 as the next value, and it occurs 1 time. I'm going to put up 9 as my next value, which occurs 3 times. And I'm going to put up 1 finally, which occurs 1 time. And I'll leave the last column for totals. Okay? So I would suggest you put up a table like this if your data has frequencies. Now, what is summation Fi? Underneath here, I'm going to put summation Fi from I equals 1 to what? 1, 2, 3, 4, 5, 6, 7. From I equals 1 to 7 in this case. And when you sum up all your frequencies, 1 plus 1 is 2, 2 plus 3 is 5, 5 plus 1 is 6, 6 plus 1 is 7, 7 plus 3 is 10, 10 plus 1 is 11. So if we are correct, that is what we'll have. Now, I'm going to create a column for Fixi because this will help you compute your arithmetic mean, the product of your frequencies and your data entry. So 3 times 1 will give us 3, 2 times 1 will give us 2, 4 times 3 will give us 12, 5 times 1 will give us 5, 8 times 1 will give us 8, 9 times 3 will give us 27, and 1 times 1 will give us 1. So let's add. 27 plus 3 will give us 30, 30 plus 2 will give us 32, 32 plus 2 will give us 34, 34 plus 10 will give us 44, 44 plus 5 will give us 49, 49 plus 8 will give us 57, and 57 plus 1 will give us 58. So we should have summation Fixi as 58 from 1 to 7. Now, we would come over to this point here and compute all the deviations from the mean. So this will be deviations from the mean. Xi minus X bar. Okay? Now, if you have Xi minus X bar, what does that mean? It means we'll start subtracting from our mean. Our mean would be, let's compute our mean here. X bar equals summation Fixi from I equals 1 to 7 in this case, all over summation Fi from I equals 1 to 7. And this will give us what we had, 58 divided by 11. And let's see what that gives us. 58 divided by 11. So 58 divided by 11 gives us approximately 5.27. To 2 decimal places, 5.27. So once you get your mean, compute deviations from your mean. So I'm going to start with 3 minus 5.27 gives us minus 2.27. 2 minus 5.27 will give us minus 3.27. 4 minus 5.27 will give us minus 1.27. 5 minus 5.27. This will give us minus 0.27. Then 8 minus 5.27 comes to give us 2.73. Then comes 9 minus 5.27, which of course should give us 3.73. Then comes finally 1 minus 5.27, and that should give us minus 4.27. So these are all the deviations we've obtained from the arithmetic mean. So after doing this, you will now compute Fi, Xi minus X bar. So let's clean this result. I'm going to bring this result over here, approximately 5.27, and add a colon here for deviations times the frequencies. So let's compute that quickly. So this will be Fi Xi minus X bar. So compute that here. Here we shall be using our deviations to multiply our frequency. So this times 1 will give us minus 2.27. This times 1 will give us minus 3.27. This times 1 will give us minus 4.27. That is using the deviations to multiply your frequencies. Then comes this. So let's minus 1.27. This times 3 will give us minus 3.81. Then minus 0.27 times 1 will give us minus 0.27. Then 2.73 times 1 will give us 2.73. And finally, 3.73 times 3, let's see what that gives. It would give us 11.19. Okay, so you end up having these values if we are correct. Summation fi xi minus x bar is what comes next. So let's compute this. We'll add all these values to get a result. So, and that should give us this result. MD equals, this is giving us 0.03. Okay, so it means that this numerator, when you sum all, will give you 0.03 divided by summation fi, which we had gotten earlier to be 11. So dividing 0.03 by 11 gives us what? It will give us our result as 0.0027 approximately. Okay, so we are going to get this result, which is very, very close to 0, as our mean deviation. Okay, now you might be wondering, earlier I had told you that the mean deviation should give you 0. If you do not approximate, it will give you 0. The reason why we are getting our mean deviation as something different from 0, that is the sum of all deviations from the mean not giving us 0 in the numerator, is simply because we approximated. So these values, the value we had here, 5.27, is where that problem is coming from. So what am I saying in a nutshell? When you approximate, the mean deviation will not give you 0, okay? Because the sum of all deviations in the numerator from the mean will not give you 0. But when you do approximate, the mean deviation will give you a result very, very close to 0, but not 0. Now let's move over to the next measure of dispersion, being the absolute mean deviation. Now, the absolute mean deviation comes as somewhat a better measure of dispersion compared to the mean deviation, in the sense that it helps overcome the problem of the sum of all deviations from the arithmetic mean giving you 0 in the numerator, which of course amounts to the mean deviation giving you a 0 value, which is elusive in nature, implying that the mean deviation giving you a 0 value tells you that there is no problem or dispersion in the data set, whereas that there might be. So to overcome that disadvantage, we introduce the absolute mean deviation, in which case the absolute value of all deviations from the arithmetic mean is taken, hence avoiding the sum of all deviations from the arithmetic mean giving you 0 in the numerator. However, the absolute mean deviation creates a problem by doing this, because it automatically changes all negatives to positive. On what grounds? So let's see how we compute the absolute mean deviation. Take note, just like the mean deviation, the absolute mean deviation can also be used to compute for cases where there are frequencies in the data set. But we might just consider how to use it for a case without frequencies, okay? So let's see. So the absolute mean deviation, AMD, can be computed with the formula summation from I equals 1 to n in absolute value xi minus x bar all over n if there are no frequencies, or it might be computed with the formula summation from I equals 1 to n fi in absolute value xi minus x bar all over summation fi from I equals 1 to n. So these two can be used to compute the absolute mean deviation. Let's start with the first one. So let's assume, as an example, let's call this example 3. We are asked to obtain AMD for the values 1, 5, 7, 3. Let's take a very simple example. So if I'm to do this as my solution, I would simply compute the following. So AMD will be equal to xi, which is 1 minus the mean. Now let's come over here and compute the mean of this data set. So this will be 1 plus 5 plus 7 plus 3 divided by 4. Okay, the average of this data set is the arithmetic mean. 1 plus 5 is 6, 6 plus 7 is 13, 13 plus 3 is 16, and 16 divided by 4 will give us 4. So it means that the arithmetic mean is 4. Subtracting the arithmetic mean from every data set in absolute value will give us our numerator in the absolute mean deviation formula. So this will be 5 minus 4 plus 7 minus 4 in absolute value this time around, and 3 minus 4. Now please, just in case you don't know what the absolute value does, the absolute value represented by these two straight lines, when a number is put into it, returns the number as being positive, whether that number was 0 or negative. If the number is 0, it will return a 0 value, of course. But if the number is negative, it will return a positive value. So the absolute value of a negative number is a positive value. So if I give you the absolute value of minus 5 to obtain, the absolute value of minus 5 will be 5. So the absolute value changes every negative number to a positive number. For that reason, 1 minus 4 should ordinarily give us minus 3, but because in absolute value, it will give us the positive of minus 3, so this will be 3. 5 minus 4 is 1, which is positive, so the absolute value still returns positive 1, plus 7 minus 4 is 3, and the absolute value will of course return 3 because it's still positive. 3 minus 4 will give us minus 1, but the absolute value of minus 1 is 1, so we'll end up having 3 plus 1, which is 4, 4 plus 3, which is 7, 7 plus 1, which is 8. So this will be 8 over 4, giving us our absolute mean deviation as 2. Now, we have a result that is different from 0 compared to the result we had in the mean deviation case. However, is this 2 a fair reflection of the dispersion in the data set? The answer is a big no, because it is also elusive. Why? How did we obtain this 2? We obtain this 2 by ensuring that all negative values in the numerator, which are deviations from the mean, would give us what? Positives. And in doing that, we have created a bias. So the absolute mean deviation has been obtained to be 2, but it does not give a fair reflection of the dispersion in the data set. For this reason, we shall consider the next measure of dispersion that overcomes all these problems in what is called the variance. Now, the variance is a measure of dispersion that overcomes the problem of the range, in the sense that it does not consider only extreme values in the data set. It overcomes the problem of the mean deviation in the sense that it does not give elusive results telling you that there is no dispersion in the data set, whereas there might be. It does not behave like the absolute mean deviation, which would automatically turn negatives to positive just to get a better result than the mean deviation. The variance is better than all these measures of dispersion in the sense that it takes the square of all deviations from the mean, in this case the arithmetic mean. Okay, so we shall be using the variance to show how the problems of these other measures of dispersions are overcome, but starting with developments on the variance. So in this particular lecture, I shall be looking at the variance, what I will call the bias form of the sample variance. So please take note of these. In this case, we will be dividing the numerator, the sum of all square deviations from the mean, by n, the sample size, not n minus 1, which is the unbiased form of the sample variance. So let's look at the variance formula. So we shall be using s squared to represent the sample variance, and since we are considering the bias form, we shall be looking at summation from I equals 1 to n, xi minus x bar all squared all over n. However, the unbiased form is minus 1 in the denominator, but this is not what we shall be using. We shall be using n. Okay, now this will be for the variance of a data set that has no frequencies. However, if there are frequencies, the variance formula will be s squared equals summation from I equals 1 to n fi xi minus x bar all squared all over summation fi from I equals 1 to n. Okay, so we shall be looking at these two formula for the variance. Now, there are alternatives to this formula for variance, and we shall be looking at how that alternative is obtained for either of them or for both of them. So let's start with obtaining that. So I'm going to put this by the side. Let's begin with obtaining the alternative. So I'm going to call it alternatives to the variance formula. Alternatives to the variance formula. Okay, so now let's assume we have s squared equals summation from I equals 1 to n xi minus x bar all squared divided by n. So to obtain the alternative starts with expanding this. So I'm going to expand what is in the bracket. When you expand xi minus x bar, which is just like a minus b all squared, the result will be a squared minus 2ab plus b squared. This will be the result. So if this is xi minus x bar all squared, then of course xi, which is your a, will be xi squared minus 2 xi, which is your a, and x bar, which is your b, plus x bar all squared. So that's the result you would obtain. So I'm going to get this result and put it in place of xi minus x bar. Now, doing that means I'm going to have xi squared minus 2xi x bar plus x bar all squared all over n. Okay? The next thing I shall do will be to now say s equals summation from I equals 1 to n. Taking summation of each item in the bracket will give me summation xi squared, and dividing by n, I'll end up having this. Taking this will mean minus 2 comes out from the summation because it is a constant. X bar comes out from the summation. Remember, your arithmetic mean is a constant, and this will be summation from I equals 1 to n of xi, and this will give me the square of a constant is still a constant. So summing a constant n times will give you n times the constant. So dividing this by n and dividing this by n gives me this. So I'm going to put this here. Okay? Now, summing a constant n times is just like saying 5 plus 5 plus 5 3 times. 5 is a constant. So if you sum it 3 times, you're going to have 3 times 5. So if you sum 5 n times, you're going to have n times 5. So if this 5 is a, this is a, and this is a, you are going to have 3a. And if it is NA, you're going to have NA. So that's what I have used here. Now, to get our final result, all we have to do is this. S squared will be equal to summation from I equals 1 to n xi all squared all over n minus this is 2x bar squared. Simply because this is the definition of the mean. The definition of the arithmetic mean says summation from I equals 1 to n of xi all over n, and that gives you x bar. When that x bar multiplies x bar, it gives you x bar squared. So you end up having minus 2x bar squared here. N of course cancels n. This will be left with x bar squared. And your final result becomes when minus 2x bar squared is added to x bar squared, you end up having your s squared variance to be summation from I equals 1 to n xi all squared minus, that is all over n, divided by minus x bar squared. And this will amount to summation from I equals 1 to n xi all squared all over n minus, in brackets, summation from I equals 1 to n xi all over n all squared, which is your arithmetic mean all squared. So this is an alternative formula to the variance this. Okay, so if you don't want to use this formula for computing your variance in the exam, you can also use this formula. Let's obtain the alternative for the second case. So to obtain the alternative for the second case, or to the second case, what we are going to do is to recall that s squared equals summation from I equals 1 to n fi xi minus x bar all squared all over summation fi from I equals 1 to n. Okay, and that would mean s squared equals, let's start with expanding, summation from I equals 1 to n fi I'm going to expand this like we did earlier on, xi squared minus 2xi x bar plus x bar squared, okay, all over summation fi from I equals 1 to n. Now, the next thing I'm going to do will be to expand using summation. So summation from I equals 1 to n fi goes with this to become fi xi squared. Then comes taking this to this will bring out x bar and minus 2. So minus 2x bar comes out summation from I equals 1 to n fi xi. Then this goes with the last one to give you x bar squared summation from I equals 1 to n fi. This will be divided by fi from I equals 1 to n summation. This will be divided by summation from I equals 1 to n fi. And this will be divided by summation fi from I equals 1 to n. By this simple law of algebra, a plus b over c is equal to a over c plus b over c. Okay? So by this law of algebra, you can divide each sum in the numerator, each term in the numerator by this denominator. So that will now mean that this will cancel this, and you end up having summation from I equals 1 to n fi xi all squared all over summation fi from I equals 1 to n, okay? Then minus 2x bar. Now take note that this defines x bar. Summation fi xi all over summation fi will give you x bar. So x bar times x bar gives you x bar squared. Plus x bar squared, which remains after cancelling this. And that would now give you s squared is equal to summation from I equals 1 to n fi xi all squared minus 2x bar squared plus this. Of course, this minus 2x bar squared plus x bar squared will give you minus x bar squared due to like terms, and you end up having this as your result. Okay? Now, this result can be finalized by simply saying summation from I equals 1 to n fi xi squared all over summation from I equals 1 to n fi minus what the mean is, fi xi from I equals 1 to n all over summation fi from I equals 1 to n all squared. So this is the alternative formula to finding the variance if given the variance with frequencies. So please take note of this. We shall be using this in solving our examples also. Now let's obtain our variance using the method of assumed mean. So by the method of the assumed mean, let's recall from my discussion in measures of central tendency. Please, you can visit my videos on measures of central tendency. So xi minus a, the assumed mean, will give you di. Okay? So let's assume that there is a governor who is sick, and in place of the governor who is sick, his deputy now becomes an assumed governor. In this case, A. Okay? So A actually is to represent X bar when we don't know what X bar is, or when we suspect that X bar may be someone like this, or when we assume this to represent X bar should X bar be unavailable for any reason. So this is just like the governor of a state being represented by someone who assumes the role of the governor. So still, just the same way we can measure the gap between X bar and XI, that is the governor and everyone in the state, whether they are enjoying good governance from him or bad governance from him, we can also evaluate this guy on that premise. So for this reason, we call the deviations from A, the assumed mean, di. So di is equal to xi minus a. So let's start with that. Now, what do we want to do here? We want to see how the variance formula can accommodate this notion. How can you compute the variance when you are given the assumed mean? That's what we want to look at. So we are going to make xi the subject of formula. So if di is equal to xi minus a, then it means that xi will be equal to di plus a. Okay? So we are now going to recall, for the first case, recall that s squared is equal to summation from I equals 1 to n xi squared all over n minus summation from I equals 1 to n xi all over n all squared. So we are going to consider this. If you recall that this is equal to this, then what we are going to do will be anywhere we find xi, we shall be putting di plus a. So I'm going to put summation from I equals 1 to n. Instead of xi, I'll be putting di plus a. So this will be di plus a all squared all over n minus, I'm going to come over here, summation from I equals 1 to n. Instead of putting xi, I'm going to be putting di plus a all over n all squared. So that will be my result. The next thing I'm going to do will be to expand and simplify. In this case, my expansion will lead to di squared plus 2a di plus a squared. That will be the expansion for this all over n minus in bracket. So expanding this will give you n squared, of course, for the denominator, and this will be summation from I equals 1 to n di plus n a. I'm going to explain why that is so. So there will be no need for square anymore. Now please take note, from indices a over b all raised to power n will be a over b raised to power n raised to power n. So this over this all squared simply means this squared over this squared. Now please take note, before squaring the numerator, summation di plus a simply means opening up the bracket with summation di. Okay, summation di is what you have, and summation a would give you na, because you are summing a constant a n times. Di is not a constant, so summing it n times will not give you ndi, but summing a n times will give you na, and n squared will come as a result of this law of indices. So that's our result. The next thing we shall do will be the next line, taking the summation each of these. So I'm going to take summation from I equals 1 to n di squared. This will be over n plus 2a summation di. So I'm going to have 2a summation di all over n, and this will be n a squared. Since a is a constant, so the square will be a constant divided by n. Now I'm going to take minus times the numerator divided by n squared will give me minus n di over n squared, minus times this will give me minus na over n squared. Okay, so at this point we can now simplify. We can simplify. So what do? We will end up having n cancelling n. So from this point, what we shall have will be s squared equals summation from I equals 1 to n. When you expand this, this will give you di squared plus 2a di, just like we've expanded before, a squared, okay, all over n. And this will be minus, this will give me summation di from I equals 1 to n all over n plus na, since you are summing a constant n times, divided by n all squared. Okay, now s squared will now give you summation from I equals 1 to n di squared all over n plus 2 na di all over n. Okay, I'll take my summation here from I equals 1 to n di. Now take note that summation brings out 2a being constant. Okay, it brings out 2a being constant, so you are going to have 2a summation di all over n, and summation takes this, which is a constant, to give you na squared all over n. So that is what we shall be obtaining there. Then coming over to this place, we shall have in bracket summation from I equals 1 to n di all over n, okay, plus a all squared. So that's what we shall have. So we now end up having s squared equals summation from I equals 1 to n di all squared over n plus 2a. We are going to call summation di all over n d bar. Okay, of course we can do that because summation xi all over n gives you x bar, and this will give us a squared minus, so this becomes in bracket d bar by what we've just done plus a all squared. So simplifying further, we have s squared equals summation di from I equals 1 to n over n plus 2ad bar plus a squared minus in bracket d bar squared, okay, plus 2ad bar plus a squared when you expand, of course. And if you simplify further, this will give you summation from I equals 1 to n di all squared all over n plus 2ad bar, okay, plus a squared minus times this will give you minus d bar squared, minus times this will give you minus 2ad bar, and minus times this will give you minus a squared, minus a squared. So you would notice that a squared minus a squared goes, 2ad bar minus 2ad bar goes, so we end up having our result as summation from I equals 1 to n di squared all over n minus d bar, which is the same as summation from I equals 1 to n di all over n all squared. So this is the formula to use if you want to find the variance in the presence of an assumed mean without frequencies for your data entries. Let's go over to the case with frequencies for our data entries. Now, for a case with frequencies, s squared will give you summation from I equals 1 to n fi xi squared all over summation fi from I equals 1 to n minus summation fi xi from I equals 1 to n all over summation fi from I equals 1 to n all squared. This was the formula we obtained for as an alternative to our variance when you have frequencies. So we are going to introduce what we had earlier. So I'm going to put here s squared equals summation from I equals 1 to n fi. In place of xi, we will still do the same thing. We are going to be putting di plus a. Okay, remember our xi was obtained to be di plus a. So this all squared divided by summation fi from I equals 1 to n minus in bracket summation from I equals 1 to n fi. In place of this, I'm going to put di plus a. Then all over summation fi from I equals 1 to n all squared. So this will give you s squared equals summation from I equals 1 to n fi. This will be di squared plus 2ad plus a squared all over summation fi from I equals 1 to n minus, this will give you in bracket summation from I equals 1 to n fi di all over summation fi here from I equals 1 to n plus, this will give you summation from I equals 1 to, okay, a comes out since it's a constant, then summation from I equals 1 to n fi all over summation fi from I equals 1 to n, okay, all squared. Now, of course, this will cancel this, leaving you with a, and this will be d bar. So I'm going to call this s squared equals summation from I equals 1 to n fi di squared all over summation fi from I equals 1 to n plus 2a summation from I equals 1 to n fi di. This, of course, means the constant 2a comes out, fi goes in with di, and summation from I equals 1 to n. This can be divided by summation fi from I equals 1 to n. Notice that this will give you d bar plus summation goes to this one and brings out a squared summation from I equals 1 to n fi, and this will be over summation from I equals 1 to n fi. So minus what you obtain here will be d bar plus a all squared. Okay, so this ends up giving you, this cancels, of course, and you end up having s squared equals summation from I equals 1 to n fi di squared all over summation fi from I equals 1 to n, and this will be 2ad bar. This will give you plus a squared, Then when you expand this, you're going to have minus 2, you're going to have d bar squared plus 2ad bar plus a squared. Okay? So we will end up having summation from I equals 1 to n fi di squared all over summation fi from I equals 1 to n for this result plus 2ad bar plus a squared minus d bar squared minus 2ad bar plus, okay, minus a squared. So this cancels this cancels this, and you end up having your result as summation fi di from di squared from I equals 1 to n all over summation fi from I equals 1 to n. Okay, then this remaining one minus d bar, take note, is summation fi di from I equals 1 to n all over summation fi from I equals 1 to n. So I'm going to put this all squared, and that will give me my variance. Okay, that will give you your variance using the assume mean method. Now let's go over to the coded factor method. Now if you recall that xi equals di plus a was what we obtained, which came of course from di equals xi minus a. Okay, now if you divide both sides by c, this particular result will give you ui, which is called a coded factor, and this will mean cui will be equal to xi minus a, from which follows that xi will be equal to cui plus a. Now this is the result we shall be using. Okay, we shall be using this result. So wherever we find xi in our variance formula we obtain, we are going to be putting cui plus a. So I'm going to start with saying s squared equals summation xi squared from I equals 1 to n all over n minus summation xi from I equals 1 to n all over n all squared. And this would mean s squared equals summation from I equals 1 to n. What you have as xi will now be cui plus a all squared all over n minus, this will be summation from I equals 1 to n. What you have as xi will be, let's use a square bracket for this. This will be cui plus a all over n all squared. Okay, so next I'm going to do this. Expanding that will give me summation from I equals 1 to n in bracket c squared ui squared plus 2 ac ui plus a squared, okay, all over n, and this will be minus in bracket. Now summation cui brings out c summation ui from I equals 1 to n all over n plus summation a gives you na all over n all squared, and n cancels this. This of course will give you u bar. Okay, so let's work from there. Now working on from there, you end up having your result as s squared equals summation c squared ui squared. I'm going to put this here. Let's bring that backward. S squared equals summation from I equals 1 to n c squared ui squared, okay, all over n. Of course we can even bring this out. I'm going to bring this out, c squared summation ui squared from I equals 1 to n all over n. Okay, then when it comes into this, you end up having the constant come out. 2ac comes out as constant. You have summations from I equals 1 to n c ui all over n, which is u bar of course. Then plus we are going to have summation a squared will give you na squared. So I'm going to bring this na squared over n, which of course cancels to give a squared, minus bringing this, you end up having cu bar, because this is u bar plus a all squared, and s squared will give you c squared summation from I equals 1 to n ui squared all over n minus 2ac u bar plus a squared, okay, minus in bracket, when you expand this, you end up having c squared u bar squared plus 2ac u bar plus a squared. And if you simplify further, you are going to end up having this. S squared will give you c summation ui squared from I equals 1 to n all over n minus 2ac u bar will cancel this. We'll cancel this. When you expand this bracket, minus times this will give you minus, okay, this is supposed to be plus. Then this minus this goes. Then a squared minus a squared will go. So you'll be left with c squared u bar squared. And your final result becomes c squared in bracket summation from I equals 1 to n ui squared all over n minus u bar squared, which is summation ui from I equals 1 to n over n all squared close bracket. So this will be the alternative. This formula here will be the alternative to obtaining the variance when you are asked to use the coded factor in the presence of no frequencies for your data entries. So we shall move on to the case of frequencies for your data entries, after which we will now solve problems using this formula we have developed. Okay? Now, if we were to compute the variance using the coded factor method, we will end up having s squared equals summation from I equals 1 to n fixi squared. That is in the case of frequencies from I equals 1 to n minus summation from I equals 1 to n fixi all squared all over summation fi. This was the formula we obtained from our development earlier on. So if we are to compute the variance using coded factor method in the case of frequencies, we are going to end up having summation from I equals 1 to n. Remember, we ended up having fi, this xi, remember, so we had xi equals di plus a, okay, which meant that di will be equal to xi minus a, and over c meant that ui will be equal to xi minus a. When you multiply by c, you end up having this. So if you make xi the subject of formula, you end up having cui plus a. So this is what we use for xi. So I'm going to put this in place of xi. So I'm going to have cui plus a all squared all over summation fi from I equals 1 to n. Then this will be minus in bracket. So I believe we can clean this off now. This will be in bracket summation from I equals 1 to n fi xi all over summation fi from I equals 1 to n. Okay, so in place of xi, we are going to be putting cui plus a close bracket all squared. So that's what we are going to have when we replace xi with cui plus a. Now s squared goes on to become from I equals 1 to n fi c squared ui squared when you expand plus acui plus a squared close bracket all over summation fi from I equals 1 to n minus this in bracket will give you summation from I equals 1 to n fi. I'm going to bring my c out since it's a constant, fiui. Then I'm going to have here I'm going to have a summation fi from I equals 1 to n all squared all over summation fi from I equals 1 to n. Good. So next we would expand this further. So c squared comes out summation from I equals 1 to n fiui squared is what we will have there, plus ac or ca comes out. You end up having summation from I equals 1 to n fiui. Then you end up having a squared here, summation fi from I equals 1 to n. divide each of them by summation fi, you end up having this. That is by this denominator, summation fi from I equals 1 to n, and this by summation fi from I equals 1 to n. So this will cancel this. This, of course, is u bar. So I'm going to put here s squared equals c squared summation from I equals 1 to n fi ui squared all over summation fi from I equals 1 to n plus cau bar, okay, for this result here times ca, then plus a squared. Then let's come back to this result. Here you would have minus c summation from I equals 1 to n fi ui all over summation fi from I equals 1 to n, okay. That will be what you have there, plus a is what will be left here because summation fi will divide summation fi, and this will be all squared. So bring that result here, you would end up having minus in bracket cu bar, since all these will be u bar, cu bar plus a all squared. So from this point we have s squared equals c squared summation from I equals 1 to n fi ui squared all over summation fi from I equals 1 to n plus cau bar plus a squared minus in bracket c squared u bar squared plus 2a cu bar plus a squared, okay. That will be your expansion, and you end up having c squared summation from I equals 1 to n fi ui all squared summation fi from I equals 1 to n. Then this will be plus cau bar plus a squared minus c squared u bar squared, okay. Then plus this will be minus, when minus goes with this, minus 2ac bar minus a squared. So minus a squared will cancel a squared. Cau bar minus cau bar would cancel that. I had omitted this. This was omitted. Please kindly add that to our results. There was a 2 there. So this cancels this, and you end up having c squared summation from I equals 1 to n fi ui all squared all over summation from I equals 1 to n fi plus minus rather c squared u bar squared. And of course you can now see that c squared is common. Bringing it out, you end up having summation from I equals 1 to n fi ui squared all over summation fi from I equals 1 to n minus u bar, which is summation from I equals 1 to n ui all over n. I'm going to put my frequency here, fi ui all squared, okay, for u bar squared, close the bracket. And this will be your formula for the variance using the coded factor method in the presence of frequencies. Now, without waste of time, we can now conclude with the following measures of dispersion, standard deviation. Now, for this, I'm not going to waste much of your time. All I'm going to tell you that s squared, if it represents the variance, can be of any of the forms we've taken previously. So, what then is your standard deviation? Standard deviation, in this case for sample variance that is of the bias form, will be the square root of the variance. So whatsoever method you use in obtaining your variance, the standard deviation can be obtained for that same problem by taking the square root of the variance. So take the square root of any of your variance formula, it will give you the standard deviation formula from which you can obtain the standard deviation, and that's all I'm going to be saying on the standard deviation. Then comes the next measure we talked about, being interquartile range. Now, just in case you don't understand the components of the interquartile range, please visit my video on measures of central tendency. So what is the interquartile range? Interquartile range, which can be written as IR, is obtained when you subtract what we call Q1 being the lower quartile from what we call Q3 being the upper quartile. So for any data set of data entries being a data set, you can obtain the lower quartile Q1, also called the first quartile, from the upper quartile Q3, also called the third quartile. Okay, so once you take this deviation from the first quarter of the Q3, you end up having your interquartile range. It is as simple as that. So I'm going to be showing you how to get that done. Then comes your semi-interquartile range. Semi-interquartile range. Okay? So your semi-interquartile range can be put as SIR. And SIR will be whatsoever you obtain as your interquartile range divided by 2, which means that semi-interquartile range is interquartile range IR divided by 2. Okay? So it is as simple as that to get your semi-interquartile range. This, and these are all measures of dispersion. Now, we'll consider the coefficient of variation being the last measure of dispersion we shall be considering in my class. So CV will be equal to S, the standard deviation all over X bar times 100, which is S over X bar percent. Okay, so it is the comparison of the standard deviation to the arithmetic mean times 100. Okay, so that is what we shall be considering, and we shall be using these to make computations immediately. So let's consider an example from which we can actually find the variance, the standard deviation, and then move on to taking other examples with which we can find this. Okay, now we shall be computing the variance, standard deviation, interquartile range, semi-interquartile range, and coefficient of variation for the data below. Okay, this will be example 4. So let's quickly get that done. For us to solve this problem, what we have to do is to reconstruct this table. So I'm going to reconstruct the table as follows. Okay, so quickly, 1, 2, 3, 4, and 5. So I'm going to make the last row my total. Okay, so let's begin from here. Now, for the first column, I'm going to put my xi, which is 2, 6, 3, 4, 7. For the second column, I'm going to put my fi, 3, 4, 7, 5, 5. Okay, and I'm going to sum my totals. Summing my total gives me 24. That's my fi. Summing them gives me 24. Now, please take note of the fact that whatsoever we are doing here comes directly from the formula for each of these items. So, for the variance formula, we will be needing the mean. So, since we'll be computing the mean and there are frequencies involved, it means we'll need a column for fi, xi. And this will give me 2 times 3, which is 6, 6 times 4, which is 24, 7 times 3, which is 21, 4 times 5, which is 20, and 7 times 5, which is 35. All amounting to 106. Okay, so this will give me 106. Now, coming over here, we will be needing a column for xi squared. Why is that so? In our reformulation of the variance formula, we will be using summation fi xi squared all over summation fi minus, in brackets, summation fi xi all over summation fi all squared. So we'll be needing xi. For this reason, I'm going to square all that is in fi. 2 squared will give me 4, 6 squared will give me 36, 3 squared will give me 9, 4 squared will give me 16, and 7 squared will give me 49. Now, adding, I'm not going to be adding this up, of course. I'll quickly go to the next column to make for fi xi squared. Here, I'm going to be multiplying all our xi squared values with fi. 3 times 4 will give me 12. 4 times 36 will give me 144. 7 times 9 will give me 63. 5 times 16 will give me 80. And 5 times 49 will give me 245. Okay? So when you add this up, what would it give us? When we add 12 to 144 to 63 to 80 to 245 to get our summation fi xi squared, we are going to have 544. So coming over here, what else do we need? Now we have all we need to compute the variance and the standard deviation. But for the interquartile range, we'll be computing with Q3 minus Q1, and Q3 is the quarter, the third quarter. Now I'll be doing something here quickly, where I'll be reordering everything we have here. Okay, so I'm going to be reordering everything we have here. So let's see. So in ascending order, let me put a demarcation here quickly. So before doing that, I'm going to put a demarcation here, and I will call this my Fi again. So I'm going to reorder my Fi to have 2, 3, 4, and 6 and 7. Of course, in this case, I'll have my frequencies as 3 for 2. I'll have my frequency 7 for 3. I'll have my frequency 5 for 4. I'll have my frequency 4 for 6, and of course 5 for 7. Now the essence of doing this is to ensure you get the correct result for your quarters. So after doing that, I'm going to put cumulative frequencies corresponding to Fi. So this is what I'll be doing. Okay. Now, for my cumulative frequency, the first cumulative frequency and the first frequency should be the same. So this will be 3. Then 3 plus 7 gives me 10. 10 plus 5 gives me 15. 15 plus 4 gives me 19. And 19 plus 5 gives me 24. So these are my cumulative frequencies. Of course, summation Fi still remains 24. Now, after doing this, we can now start solving our problem. Starting with A. We are to obtain the variance, and the variance S squared is summation from I equals 1 to n Fi xi squared all over summation Fi from I equals 1 to n. And this will be equal minus summation Fi xi from I equals 1 to n all squared all over summation Fi from I equals 1 to n. Now this gives us summation Fi xi will be 544 all over summation Fi, which is 24, minus in bracket 106 over 24 all squared. So this will give us 544 divided by 24 gives us 22.6, 22.67 to 2 decimal places. Then 106 divided by 24 gives us 19.51. Okay, when squared, right? 19.51 when squared. Now, subtracting this from this gives us 3.16. Okay? 3.16. That will be our result for the variance. And quickly, we can now obtain our standard deviation, which is the square root of your variance. And that will be the square root of 3.16, which gives us 1.78 to 2 decimal places. So I'm going to put an approximation there. Now that we've obtained our standard deviation, we can now move on to getting our interquartile range. So, for our interquartile range, being question C, we start with saying Q3 is 3 over 4 n cumulative frequency value. And that will give us 3 over 4 times 24, which is our n. Okay? Your n in this case is taken as the summation of all frequencies. So please take note of that. So let's change this rather to capital N for reason of no confusion. And I'm going to have here cumulative frequency value. So this will give us the 18th cumulative frequency value. And that's where this particular table comes in. So don't get it from this table. Rather go to this other one that has been arranged in ascending order. Now, the 18th cumulative frequency value is greater than 3, greater than 10. 18 is greater than 10, greater than 15, but not greater than 19. And when you trace this down, you end up having, when you trace 19, the cumulative frequency value, down to the number here, the data entry it corresponds to is 6. So it means 6 will be your 18th cumulative frequency value. Okay? 6 will be your 18th cumulative frequency value, hence your third quarter. Now, let's move over to Q1. In a similar manner, we are going to compute Q1, but Q1 is 1 over 4n cumulative frequency value. And that will give us 1 over 4 times 24 cumulative frequency value. And that will give us 6, the 6th cumulative frequency value. Now, we'll come over here. 6 is greater than 3, but not greater than 10. So tracing from 10 down to 3, you'll notice that 3 happens to be your Q1, your upper quarter. And that now means, quickly, you can see that now means that your interquartile range will be equal to Q3 minus Q1 which is equal to 6 minus 3, giving you 3. So that's your interquartile range. Now, to get D, your semi-interquartile range, is simple because we were told that semi-interquartile range is interquartile range divided by 2. And that means that 3 divided by 2 will be your result, which is 1.5. And that is as simple as that. Then we now come over to E, being the last problem. We have to find the coefficient of variation. Now, in the course of this video, I told you that the coefficient of variation compares the variance to the mean. So, in percentage. So that will be standard deviation over, it compares the standard deviation to the mean in percentage. So that will be standard deviation over the mean times 100. And that gives you what we got as our standard deviation, 1.78, divided by what we got as our mean. Please take note, we may not have computed our mean in isolation, but our mean was actually 106 divided by 24. What did that value give us? 106 divided by 24 is our mean. Summation fi xi. So that will be 4.42 times 100. So dividing 1.78 by 4.42, multiplying it by 100 gives us 40.27% approximately. Okay? So please share the video, like the video, and endeavor to go through what we've done. Check the problem. If there are errors, please let me know in the comment section. And if there is any complaint or anything you want to say about this video, about anything you've learned, if you want to ask questions, please drop your comment in the comment section. Thank you very much. Until some other time, this is GER Hub. Stay blessed.